Okay, let's talk about the Riemann mapping theorem, which is a really an amazing term. It's and it should be sort of the pinnacle of a course like this in one complex variable. It's one of the amazing things is how easy it is to prove, given how how much of a powerful statement it is. So let's just see the theorem. Suppose that you have a simply connected domain, any simply connected domain. The only exception is that it's not all of C. Right? So there's lots of simply connected domains, and the only one that we're not taking is all of C. Now take any point P in U, then there exists a biholomorphic map from U to D such that f of P is 0. So that means that U and D are biholomorphically or conformally equivalent. It means that there exists, this map F is bijective and its inverse is holomorphic. Now, this map is also unique in the sense that it's the unique map such that f prime at P is real and positive. Now, this this notation f prime of P bigger than 0, right, that doesn't mean that we can compare complex numbers, right? It's just a shorthand of saying it's real, and as a real number, it is positive. So if the derivative is positive, and we can always once we have such a map, we can always make it real and positive. Then such a map is unique. Okay. Now, how are we gonna get? Get such a mapping? Well, we're gonna do it by looking at a family of maps, a set of maps. So take injective holomorphic maps that take P to 0, right? And we're gonna call that script F, right? Now, among these maps, what we're gonna do is we're gonna maximize the modulus of f prime at P. Why do we do that? Well, we're sort of the intuition is that you want to sort of fill in as much of D with f of U should be as much of D as possible. Well, that should be I want to spread out as far as possible, so that I should be able to do it with the largest velocity, right? I have the largest velocity at P. That seems like I should get the furthest, right? That's the intuition. But the way it's gonna work is we're gonna basically in this set we're gonna approximate the supremum of the f prime at P, and then Montel is gonna give us a conversion sequence, and the limit of that sequence, well, because what Montel gives us is convergence is uniform on compact subsets. That actually means that it's that f prime is also conversion. So this limit is going to actually maximize f prime at P, right? And this limit is going to be our map, right? We're going to prove that if a map in F is not onto, then we can find one with a larger derivative at P, right? So that means that if we're looking at the maximizer, and Montel is going to give us that the maximizer exists, then we have our map, right? It has to be onto. But the first thing that we need to do is prove that F is not empty, and this is actually where this restriction that U is not C comes in. Because if U was equal to C, then we'd have a map from C to D, right? From the complex plane to the disk, and the only such map by Liouville is a constant map, right? And that's not going to be even injective, right? So there clearly isn't such a map for the complex plane, but it's interesting that every other domain has such a map. Every other simply connected domain. So suppose that that U, while U is not C, and so there has to exist at least some Q in the complement. Now, if the complement was actually big, if it, in particular, if it contained a disk, then what we could do is we could do sort of this translation and inversion that would give us a bounded map, so we could make it go into the disk. This is basically just like in the proof of Cassarati-Weierstrass. But well, we probably not as lucky, because, for example, the slit plane is simply connected, but the complement does not have an open set. So we can only assume that there is a single point Q that's not in U. So we look at the function z minus q, and since U is simply connected, we can find a square root. We can find a G, so that G squared is z minus q, right? Because z minus q is not 0 on U, and U is simply connected. All right. Now, G of U is an open set, right? Open mapping term. Now, if G of Z is equal to G of W, that means that G of Z squared is G of W squared. Well, G of Z squared is Z minus Q, and G of W squared is W minus Q, so therefore Z equals W, so that means that G is injective. Okay? But there's more. It's not only injective, it's well, it's more than that. It's if I take the same argument and I look at G of Z equals minus G of W, well, that still implies that G squared, G of Z squared equals G of W squared, which still implies that Z equals W. Well, if Z equals W, then G of Z is equal to G of W. Therefore, G of W is equal to minus G of W, and the only number which is equal to its negative is 0, and G is never 0. So G of Z is never equal to G of minus G of W, right? Which means that G of U, the image of the entire U, it does not intersect minus G of U, right? So the negatives of all the points in G of U, or the image of of U under minus G as a mapping. Now, G of U is open, so minus G of U is also open. And minus G of U is in the complement of G of U. So the complement of G of U is now, that is open, right? The complement of U maybe wasn't, but the complement of G of U is. So there is a disk. Well, it's not open, but it contains an open set. Sorry. So there is a disk, right? Let's call it delta R, centered at Xi. So now we can do that inversion. Again, that's just like in Cassarati-Weierstrass. And so this map takes U to D, and we can, by composing with the right automorphism, this inversion might not take P to 0. It's going to take it to something, but we can make that something go to 0 by sticking in the right automorphism. In other words, we've proved that F is non-empty, right? And the idea of this proof was that what does the square root do? The square root takes complex numbers and it halves the argument. So it takes the complex plane and basically takes it to sort of half the complex plane, right? And so it's, even though U maybe was a big set, G of U, which is, there's the square root is injective, so it's essentially the same set, right? Now we had it was only contained in kind of size-wise half of the complex plane, and so we could find a disk in the complement, and now we were, now we could go on, right? All right. So let's prove this, that the maximizer of the derivative is onto. So suppose that f is in f, so it takes p to 0, it's injective, but it's not onto, right? So that means there exists a q, not different q than before, in the disk, which is not in the image of f. And let phi sub q, that's just the standard automorphism of the disk that takes q to 0, right? Now, just like before, there exists a g, again, different g than before, such that, which is a square root of phi sub q composed with f, right? Because f never went to q, and that was the only thing that could go to 0 after hitting it by phi, right? So this square root again exists by simple connectedness of u. G still takes u to d because the square root of a complex number in the unit disk is a complex number in the unit disk. If g of z is equal to g of w, then f of z is equal to f of w. It's very similar to before, right? Because, well, if g of z is equal to g of w, the squares are equal, and and phi sub q is just an automorphism, right? So just from the formula for g squared, we get that f of z is equal to f of w. Now f is injective, right? So that means that g has to be injective. So, in particular, if g of z is equal to g of w, we get that z is equal to w. So g is an injective map. It takes u to d. Now it might not take p to 0, right? It actually takes p to some root of minus q, right? One of the two square roots of minus 2. Minus q, sorry. So if I compose it with an automorphism that takes this root, so whatever g of p is, to 0, then I get a map that takes p to 0, and therefore is in script f. Now, if so if we wrote h with in terms of some automorphism and g, we can just solve what the inverse is, right? It's phi of minus g of p, so we can solve for g, and now we can differentiate. Well, let's differentiate. Let's differentiate basically g squared. At p, right? And let's recall this was an exercise, but it's just simple calculus. At 0, if I have one of these phis, we know the derivative is 1 minus the modulus squared of whatever the point taken to 0 is. Okay, so if we take the derivative of the phi sub q circle f at p, we had this guy over here. Now, f of p is 0, and we know what phi prime at q is. So we're getting this thing over here, right? Now this is also g squared. So if we differentiate g squared, just regular calculus, then we get just by chain rule, and now we plug in. Now we've solved for g, right? So we plug in, and again, we use that h of p is 0, right? So there's this 2 g of p becomes this again because there's h of p over here, right? And then g prime again by chain rule it's going to be this guy over here, and now we can just solve this, right? Oops, the wrong direction. So if we plug in those zeros, right, write down what these two terms are, we just get this formula over here, right? All right. So now we really want to figure out what is f prime in terms of h prime, right? So we're interested in the modulus. Now, g of p squared is minus q, right? That comes up, just plugging in z equals p over here, right? So fp is 0, so plugging in 0 into phi of q, I get minus q, right? And so therefore, if I solve for the modulus of f, I get this. But now this modulus of g of p squared, that's just the modulus of q, right? So I have 1 minus modulus of q on top. So if I solve, if I cancel out things, I will get that's the coefficient in front is 2 times the square root of q divided by 1 plus modulus of q, and here q in modulus is less than 1. I mean, it's in the disk. It's a fixed point inside the disk. Therefore, this factor before is less than 1. So in particular, f prime at p in modulus is strictly less than h prime of p. Okay, so we've shown that if f is not onto, then there is actually then it does not maximize the derivative at p. All right, so now we can go to Montel. We construct a sequence f sub n in f such that the limit of the derivatives goes to the supremum. So whatever the supremum of all the derivatives is, we can find it as a limit of a sequence. Now we don't know a priori what this sequence does as functions, but we can apply Montel and get a convergent subsequence, right? And convergence meaning here converging uniformly on compact subsets. Now we could, without loss of generality, we could just assume that f sub n is that convergent subsequence, right? I mean, it's clearly gonna still satisfy this limit over here, and so we can just assume it is convergent by Montel, and that it converges to some function, and let's call it f. Okay. By this corollary to Hurwitz, right? That said that if we had a convergent sequence of injective holomorphic mappings, then the limit was either injective or constant. Could be constant. Now here, if we take limits, and again the derivatives also converge, so clearly we get that the f prime at p is not 0, because that's easy to see that we could have started with some stupid map that is not onto, and then there's definitely something which has strictly bigger derivative. So so that means that f cannot, this limit cannot be constant, right? It was clearly, we can even construct it as an increasing sequence. Now now it's even easier, right? I mean, all those fn's are in script f, so f at p is also 0, right? Limit of 0 is 0. And we get that just by taking limits, we get that just using continuity, that the f, the image has to be at least in the closed unit disk. But this is a holomorphic map, so open mapping theorem says that it's actually in the open unit disk, right? That f takes u to d, right? Now f must be onto, because if it was not onto, then we could construct something with a larger derivative at p, and we know that this is the maximum, right? There is no larger, there is no f with a larger larger p, larger derivative at p, right? One of the things that we've actually, which Montel proves, is that the supremum is actually finite, right? Because it is the f prime at p of some function, right? And that function, that's the largest it can be. There is nothing larger, so this must be onto, right? So that's the proof, right? It's once we have onto, we have the map, right? Now uniqueness is left as an exercise. I mean, clearly we can always make this real and positive by just multiplying f by e to the I theta for the right theta. But the uniqueness, well, I'll just leave it as an exercise. I won't ruin it by giving away the answer. Now, a couple of remarks. This theorem doesn't tell us how to construct such a map. It just says that such a map exists. And actually, these maps are quite useful. It's very useful to be able to map a certain domain to the disk. It makes, we can write down, for example, for solving some differential equations, you can write down, it's much easier to work in a disk, which is a very, easy domain. You can solve a certain differential equation in the disk, and as long as it's, something like the Laplacian that works nicely with conformal mappings, then you can use that to solve in any simply connected domain. However, for it to be useful more than existence or something, then you need to actually know what that map is. Now, there are actually there's lots of books that all they have in them is various conformal maps, right? So this is, people have been, especially at a certain point, people were very concerned with trying to get conformal maps basically for any reasonable domain, not just simply connected, but for simply connected, you'd want to get to the disk or upper half plane or something like that. But so there's a whole industry of constructing these maps. For example, there's an explicit formula, or if you have a polygon, polygonal domain, that there's an explicit formula that that gives you this map. So it's a little complicated, but there is an explicit one. Now the other thing that it doesn't tell you how nice the map is as you go to the boundary, right? It could be really, really, really bad as you get close to the boundary of U. But it's generally actually is quite nice. It turns out that if the, for example, if the domain has a nice boundary, like a Jordan curve, so you're sort of going around nicely around the boundary, and the domain is always on your left, and what's outside is always on your right. Then the map will actually be continuous on the closure, so it will extend continuously up to the boundary, which is quite useful if you're if you're solving some problem. You know where the boundary goes, right? You can identify the boundary points of the disk with boundary points of the domain. And there's even more. If the boundary is smooth and the mapping extends smoothly to the boundary, right? So you can even take derivatives along the boundary, or take limits of derivatives as you get close to the boundary. And if the boundary is real analytic, it even the mapping actually extends past a little bit as a holomorphic mapping. So it's really a holomorphic mapping of something that contains U, that goes into something that contains the disk, right? Contains the closed disk, including the boundary. Okay. Again, we're not gonna sort of touch these questions, although they are definitely important in a lot of the applications of this theorem. But we're just thinking of just the Riemann mapping theorem, and actually we'll next time we'll see an interesting application of the Riemann mapping theorem that might not be it's not the standard way of proving that result, but it's kind of an interesting interesting how you can use Riemann mapping theorem and the sort of the niceness of the disk to prove all sorts of things. All right.